All right, so we talk about the Hamilton-Jacobi equation, which is here. It has the action on it. And then what we want to do with this, we talk about it too. Basically, we have, this is the equation that tells us about how things evolve in time, given the Hamiltonian. And then we look at what things were satisfied with the Hamilton-Jacobi equation. In this case, we said we have that this guy is equal to this differential as it was required. And we were looking at whether this, the Hamilton-Jacobi was recovering mechanics, classical action, just as we did before, right? So we have that. We have shown that it works well. Now let's talk about what we did. We have a second order differential equation for the time evolution on configuration space. That's Lagrange equations. We also have first order differential equations for time evolution in phase space. That's the Hamiltonian equation, Hamilton's equations. And now we have the Hamilton-Jacobi approach that has an integration constants for first order differential equation in configuration space. That makes sense? Those are the things that we have, right? So we had n second order differential equations. We had 2n first order differential equations. And now we have n initial conditions and first order differential equations. So they're basically giving you the answers, the same answers, or should give you the same answers. But they're really more compact ways of doing things. So let's continue with this. Questions before I start? Katie, questions? We're all good? All right, awesome. So what happens if the Hamiltonian is conserved? So if we have that the Hamiltonian is conserved, we would get that this thing is equal to 0. And what does that mean? That the Hamiltonian is time, doesn't have a time dependence. You guys know this already, right? What is it? Look.
Another thing?
Huh?
Another thing?
No, what does it mean?
Oh, if there's no time dependence on energy.
Energy is conserved, exactly, right? So if we do that, so this is the total energy. If we have that, then the Hamilton-Jacobi equation has a simple form, and we can use it because we're going to come up with this equation right here. We have this solution that doesn't depend on time minus the total energy, right? Because your Hamiltonian H becomes just a quantity that is conserved, the total energy, times time. So in this case, this is a constant. And then since the time dependence has dropped out, your Hamiltonian, right, is going to depend on Q, on how this zero order W behaves, and not time. So you see this one right here, your Hamiltonian has a time dependence. For this one, your Hamiltonian is just the energy, so there's no time dependence in the Hamiltonian. And then we also have this guy right here. This one is Hamilton's principal function. And the important thing is that every path in configuration space is determined with this Hamilton principal function. All of them have the same energy. So you take a path, right? And every path that is determined by this guy, so you take the path right here, right? And this is the Q's on the path. You have this path. They're all going to have the same energy because they're constructed with the same W up. And how do we construct a solution based on this equation right here? So you can think of having a system that actually has planes going around like this. And you have that these are different levels of W. Each of them is there as a different level of it. Since we have that the potential, this is the potential, right? This potential is determined already, and you know what this potential is, and that potential, whatever it is, whatever coordinate you have there, is the one that determines your W. So we also have there's the momentum, and this one is determined by this guy, 0 right here. Sorry, did I put the 0 in the wrong place? Yeah. So 0 up here, and this is your momentum. What happens is that this path that is taken is going to have that is perpendicular to this motion. So the motion is going to be perpendicular in this surface right here that is passing through here. The motion is always perpendicular to it. So well, this is supposed to be a straight line. It's curving a little bit so that it has this perpendicular to this point on the surface. And then here it's also going to bend a little bit, but it's perpendicular to the surface. So you have that this W gives you the surfaces that you're passing through, and wherever you come out, the direction that your trajectory is going through. So you're going through this trajectory, right? Right there, that trajectory is perpendicular to this different W surfaces that you have, where those W's are determined to be the constant energy values. All right. Questions up to here? No? So I have a last question, a last homework set for you guys. It's going to be due on Tuesday next week, not tomorrow. And it was actually a bit tough to write because going through the problems in Goldstein, the problems I feel that they go, there's a path between 2 points that is the shortest one. That path is a straight line, draw a straight line. So that's how some of the problems start with. And then the last ones are, and then the next level of problems, which I wouldn't assign to you guys because those seem kind of silly to do, right? And then the next level of the assignment is like derive a new form of quantum mechanics. There's no sweet spot in Goldstein for this. So I had to figure out how to give you a problem that embodies things like this. And it's already took me a while. I think it's there. But basically, some of those problems are not Goldstein problems. So if you have questions about the homework, don't hesitate to ask. Maybe I'm not explaining things clearly. And that's the reason that you have questions. Let's go to the next level on this. And then I wanted to come back because I think that this is actually really important, but let me finish the course content, the book course content, and then I start on news and coming back to this Hamilton-Jacobi equation and why it's really important. So we have done action angles before. Now let's do it from the Hamilton-Jacobi. So this is the last question on your homework. So I want to give it to you so you can start it today. And actually it's really important because I feel that the Hamilton-Jacobi approach is not useful in any way. Like I already mentioned, why is a new approach. And basically that what you're doing here is the same, is going to give you the same answers as using Lagrangian mechanics, Hamilton dynamics. But now you have another way to do it, but then the problems are not going to be any easier, right? And basically, there's nothing useful about it until you start thinking, why am I teaching this, right? And then you realize because this is how quantum mechanics started. But if we look at action variables, you can see how they work in this case. What are they giving you? So another thing that is important to notice is that the problems are not super complicated. I think the most complicated problems that you got in the homeworks and exams have had to do with Lagrangians, right? Like the Lagrangian of this coupled oscillator, blah, blah, blah. You could also solve those problems with Hamiltonians, with Hamilton-Jacobi. But instead of doing that complicated problem using this method, let's do something very simple, okay? Just so that we can see how it connects to the other problems, to the other methods. So let's take a single degree of freedom, Hamiltonian, and take it through the Hamilton-Jacobi methodology so that we get to use the action angles too. So we have this Hamiltonian. This is a very simple one, so it's just going to be p squared over 2m plus some potential, some generic potential that depends on the quantity q. Things that we know right away. Time independent. So energy is conserved, right? And what is it that we get with the Hamilton-Jacobi method? We don't have to do two differential equations, right? We have to do one differential equation and set up one integration constant. So this is 1 degree of freedom, so has one integration constant. If you have 4 degrees of freedom, how many integration constants would you need? 4. All right, so we have these things. Let beta be the integration constant. So this beta, the integration constant, is a function of energy. Energy is conserved, right? So you have to set up the system in configuration space at some point where the energy is whatever it is, and the energy is not going to change. So this is your initial condition. If you have that the energy is conserved, it doesn't mean that the energy is just a single value the whole time, right? Like you can put it in different configurations to start it with, and you will have more initial energy. If you think of the pendulum, if the pendulum is started here, at time is equal to 0, the energy is 0, and it's a constant, right? If you start the pendulum here and then let it drop, it's going to have some energy, and the energy is going to be constant as it goes through motion right here. And if you start the pendulum up here, it's going to have a different energy, and that energy is also going to be constant. So it depends on your initial conditions, right? And this integration constant is basically our initial condition. Make sense? Questions? All right. So what I want to do, my objective is to show you how this integration constants work, right? And because if you're in this high level math, sometimes high level explanations that we were doing before, sometimes you miss the simplest things unless you see it in an example. So that's the goal for right now. So we have that this is the integration constant. We want to work on things explicitly. So now I have that there's this function. This function depends on my variable q, depends on the time. And it's also going to depend in beta. That's my integration constant. And this beta is actually something that depends on the energy. So this is what we wanted to do with the action angles approach. What we were doing is that we were going to do a canonical transformation. What are our coordinates here in this Hamiltonian? Q and P, right? So what we want to do with the action angles is, let's say that I don't work in Q and P coordinates, but rather, right, we want to go we want to find the canonical transformation that takes this Q and P coordinates into, let's say that our new coordinates are going to be alpha and beta. Does that make sense? So this is momentum, right? in this new coordinate system, this is the new momentum. Now, thinking about your angle, does this make sense? You guys remember what we were doing before? We were going with an angle 0 to 2 pi, right? And we were untangling this mess of lines into just making it a straight line. So does this make sense? Now you have that this is your initial condition, and it's also your new momentum. So you're rewriting, you want to rewrite the Hamiltonian in this new momentum approach. And the one question is what about alpha? What the heck is alpha now, right? I mean, I knew that this is my coordinate before, and now I have alpha. How do I get alpha? All right, let's get started with this. You guys remember how to do this? No? So what we're doing is that we're gonna change coordinates and they have to be canonical. So this has to be true. Q is now Q that is a function of alpha and beta. P is now in the new coordinate system also a function of alpha and beta. And this is the big one. If we do Q and P, this Poisson bracket, and remember that they're in the alpha beta coordinate system, this is defined to be derivative with respect to alpha of Q, derivative with respect of P of beta, with respect to beta of P, minus the opposite of it. So we have the beta now with the Q and the P with the alpha. And this has to be equal to 1. So that's because they're canonical, right? All right, just coming back to you guys, what means what we're doing, right? All that turkey washed it off. So now that you have this, we also know that P is this quantity, the partial derivative with respect of Q of this quantity. And now you have to remember what depends on what, right? So we have to remember that this W quantity is also going to be depending on this point on Q and beta, right? That's what it depends on. So we have this guy, Q depends on alpha and beta, P depends on alpha and beta, but this W quantity depends on Q and beta. Beta was our initial condition.
Q and P and alpha and beta, those are two different set of coordinates, right? Then how can we write W as a function of Q?
Right. So W is, let me go back. W is this guy. And it depends on Q, on time, and on beta. So that's why W still depends on, W is a quantity that still depends on beta and Q. So this is where we have to do the transformation, right? In the transform. So before the coordinates were Q and P, but now we're going to have new coordinates that are going to be alpha and beta. And we could write Q in terms of alpha and beta, we could write P in terms of alpha and beta. But that one, we already had it in terms of Q and beta. So now we have to figure out how do we use that and how do we do the transformation? with the transformation obeying this rule, that the Poisson bracket of P and Q is still is 1. So the commutation of those two guys, right? The data stays and follows that rule. That's the part that is canonical. So, because of this part, I can rewrite, and this is gonna take a lot of space. Let's see if I can do it here. So this is my Q and P. And I'm gonna have the DQ D alpha. And then my P is gonna turn into derivative with respect, second derivative of W with respect beta and Q plus the second derivative of W with respect to Q and then I need the derivative of Q with respect to beta. So that's the first term. And then I need this other term right here. So this one has the dq beta. And then this one, P with respect to alpha, is like taking the derivative of P, but instead of having P, sticking this derivative in here, right? So I'm gonna have just one term, and a second derivative with respect to Q twice of W, but then I still need, this is with respect to alpha, so I need the derivative of Q with respect to alpha. That makes sense, how to do the derivations? I mean, it's just, I write this one, where we know that this P depends on this, right?
One more term will be there.
Sorry?
D square W by dou alpha dou Q, that term will also be there.
Sorry, which one?
Like in the, for the second term for dp by dl, the partial derivative of P with respect to alpha, similar to the first, like first two terms, we will have one more term, right? Like first as D square W by dou alpha dou Q.
Oh, yeah, but those, so we're doing this one, right?
Yeah,
W doesn't depend on alpha.
okay.
That's why we don't have it there. Make sense?
Yeah.
Okay. All right, so we have all that. We have that action variable right there. And if we look at it, we can start seeing that things are gonna, I mean, if we multiply it out, we have alpha, alpha. We have, yeah, so we have alpha, alpha here. We have dq beta, dw, dq here. So we see that a couple of things are going to cancel out, right? So that means that this one, after cancellations, is just going to be dq, d alpha, and the partial with respect to q of w, which depended on beta. So we need to come back and say, this is a canonical transformation. So we need to look back at this point right here. So this, to be canonical, has to be equal to 1. And we have written this one, and it has to be equal to 1. And what we're after is, what is the alpha that turns this to be equal to 1? So this whole thing has to be equal to 1. And that's the question. What is alpha so that that turns into 1? So that would make it such that alpha has to be dW d beta. Does that make sense? This has to be equal to 1, right? So if I have this, and I have this alpha has to be equal to this one so that everything cancels out and you get this one and this one to cancel out into 1. So my alpha is just this guy. We're good? Yes? All right. So now that we have that, what do we have? We have a solution. We have this solution, the W, to the Hamilton-Jacobi equations that we had in Q and P. And now we have it also in alpha and beta. So we have W, the solution to the Hamilton-Jacobi equations in Q and P, and we also now have it in alpha and beta coordinates. So we have those two set of coordinates. So let's recap what we have. We have that P is equal to this guy. And we have that alpha is equal to this guy. And W is this one. This is the solution to the Hamilton-Jacobi equation. So this function W is an example of a generating function of the second kind, because this W gives you this guys. So that's just called the generating function of the second kind, in case that you're interested in the math nomenclature for this. So what do we have with all of this? If beta is the energy, and this energy is the new momentum, right, after our transformation, what does that mean? Does it make sense now? So we're in this weird thing where everything is about to click. We have that W, right? We have the W, which is the solution, is QT energy is equal to some quantity W naught TE minus energy times time. And we know that alpha is the derivative with respect to beta, right? So in this case, alpha is equal to, now we take the derivative with respect, not beta, but energy, right? Because beta is energy. And we have this guy that is a function of Q and E minus T. So I took the derivative of this whole thing with respect to the energy. This guy is here. And then the derivative of this is just T and there. So in our new momentum, in our new coordinates, energy is a new momentum. Alpha is our new coordinate of the system. So alpha is the canonical dual to the energy. And you see that it has some relation to time. Does that make sense? Is it clicking? Energy and time got together. So we have the position and momentum got together. Energy and time got together. So we see that transformation that we just did. So if we look at this, alpha is our initial starting time. And with this alpha, I have T naught, the initial time. And this alpha is parameterizing the trajectories that I have in this one-dimensional system in terms of the energy and what is my initial time. T naught. So we have that a trajectory is now parameterized by what is your energy, and this energy is going to stay constant, and at what time are you starting. Not what position are you, is your bob on the pendulum, but actually what is your initial time. So if your energy was a number, and instead of saying, and my bob started here, you just say, my energy was this much, and I started at this time, and then you can tell what the motion is. And the whole trajectory is given to you. This T naught does not depend on time. And this energy does not depend on time. T naught is just a quantity, right? It's your initial condition. Questions? No? Yeah.
One thing kind of unrelated, but is that equation up there? Like W, naught? Would that be considered a Legendre transform?
I'm sorry?
Would that be considered a Legendre transform?
Um,
Instead of using like momentum.
so I guess it's not exactly a Legendre transform, but yeah, you can think of it kind of like that. Like this is the canonical transformation to go from this to this. Yeah.
It kind of has that same form.
Yeah. Yeah.
Just with energy and time instead of.
Uh-huh. But it's just the other representation that tells you how things behave. Okay. All right. So how much time do I have? 9 minutes. Let's do another example, okay? So here is energy as beta. So this is example 1. Then let's do example 2. So now let's say that beta is equal to I, which is the action variable we had a few weeks ago. And I don't remember, a couple of weeks ago that we were doing with this new action variable I. And the question is, what is the new alpha? So we had this I as the action variable and a theta that was so that was the action variable, and we had the angle, right? The action angle was theta, I and theta. That's what we were doing before when we were untangling things and making them straight lines. So in this case, we see that beta is going to be called the action variable. That's our beta. And we have an alpha. So what do you guys think this alpha is going to be related to? So before it was energy, time, and we had taken position, it would have been momentum. Right, so this is probably going to be related to theta, right? So this is what we should get. So what we have then is that our W naught is the integral. So W is the classical path, right? So W naught is defined as this quantity. And this quantity, I can put the two together and have the integral of L plus H right here, dt. And if I do that, I can also rewrite it as Q dot P dt. So when you look at L and H, right, for this simple system, the Lagrangian and the Hamiltonian, if you added the two together, you're left with just this thing. Because the Hamiltonian is related to the Lagrangian, right? And that's the only thing that you're left with, Q dot P. And this is the time derivative of Q. This is P, and then you're integrating over time, so that you can rewrite this guy as P dq. So we had as definitions that alpha is equal to dw partial of w with respect to beta, right? And what we know is that beta is now going to be I over there, the action variable. So what that means is that I have the derivative with respect to the action variable of P dq, and here I'm also going to have the energy di times t. So this is exactly what we did up here, right? Where we took, this is W, is given by W naught minus ET. Here we have the derivative with respect to beta of W, it's going to give us alpha. And since beta is I, W is W naught minus ET. So I have this partial, boom, 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 and we have that. So if you look back at your definitions, what we have then is that alpha is equal to, and from the first one, we have the action variable, the action angle as our answer. And then when we look at this portion right here, this is omega t. So this is the frequency of the motion. This is in your previous notes about this omega, which is the frequency of the motion. And this integral, we also did it before, that was the angle. So alpha is not exactly your action angle, right? It's not quite equal to it, but it's equal to it linear in time. So that's the transformation that we have. So what does that mean? It's not exactly, what this means is that this guy is however much this changes with time, is taken into account. So this guy is, this guy changes with time, but it changes with time this much. So this guy is not time dependent. So time independent version of the action angle, because it doesn't depend on the time. So now you have that the angle is not itself what we were getting with alpha, but it's just that alpha itself doesn't change with time, because whatever this one changes by is going to be this much. So the changing time of this one is this much, so therefore this is constant in time. So the angle can change with time. This alpha doesn't. So, yeah.
I mean the same thing actually. So when t goes to t naught.
Yeah, maybe it's, yeah, I think it might be, you can say it's kind of similar, right? Like this is theta naught, and it's theta minus how much it changes with time. Yeah, kind of like the same. Because what we're doing is that we're parameterizing our trajectories, right? We have trajectories, they're being parameterized, and what we were parameterizing over before would change with time, which was the I and theta angle. The action variable could change over time. Your theta could change over time. So what we did is that we moved to, with this transformation in the Hamilton-Jacobi equation and the canonical transformation, what we're doing now is getting something that doesn't change with time. We're getting the canonical variables that do not change with time. So that W right here, you can think of it, this is the motivation actually for this. You can think of this W as a way to generate the time independent canonical variables. That's what your W is there for. It's trying to get you there. So if you want to learn more about this, the relationship between canonical transformations, angle action variables, the Hamilton-Jacobi formulation, it's all inside of Goldstein. Chapter 10 is really full with that. But that's the main thing, what this W is able to do for us. All right, so there's a new homework. I'm gonna upload it. I'm gonna check for typos right now, but if you find typos, let me know. I'm gonna upload it. You guys read it, ask me questions on Wednesday. It's due on Tuesday, but if you wanna turn it in earlier and have me check it, I can do that for you. And then next week is our final. So a couple of you have asked if we could take it earlier. So if anybody else wants to take it earlier, I'm open to that. Okay. Give you a chance for everybody to do that if you have travel plans or other things to do.
So you're trying to take the exam on Monday.
I don't know, we haven't talked about the time. I guess you guys are open to the time, right? Yeah, it's up to you guys. And if anybody else wants to take it earlier also, I'm okay with that, just let me know. Officially, we have to take it on the Friday because that's what the final schedule is. And you might be studying for other classes, so if you're doing that, probably doesn't make sense for you to take it earlier, right? But if you want to do that, I'm okay with that.